Good morning, my dear friends. Today, our topic is one of the most and interesting and very great topic, that is the law of motion. Of course, you can guess or you can recognize Sir Isaac Newton and the picture. One of the as there is a saying in English, three apples which change the human lives a lot. That is, the second apple is none other than the Newton's apple. You can see that. So we are going to discuss the laws of motion at the graduation level. Okay. So definitely you will see that at the graduation, when I use the word graduation level, your understanding will be refined, not like in our up to plus 2. So let us go to that, and what exactly Newton says about the laws of motion and everything. So, okay, the Newton laws of the motion, they describe the relationship between the body and the forces acting upon it, and the forces acting upon that particular body. Okay, and its motion in response to those forces. Okay, the first law defines the force qualitatively. The first law defines the force qualitatively, whereas the second law, quantitative measurement of the force acting on the body, will give you quantitative second law, qualitative first law. The third asserts that the single isolated force doesn't exist. No single isolated force. Like you may remember, when I use this word, you may remember that unipoles in magnetic dipoles are not available in the universe. Like that, third law asserts that a single isolated force doesn't exist. Okay, the first law, let us see into the first law. An inertial frame of reference. See, I underline this word, inertial frame of reference. An object either remains at rest or continues to move at a constant velocity unless acted upon by a force. If the external force is not acting on the body, that is the first condition. Foremost condition is the body must be in the inertial frame of reference. First and foremost thing is the body must be in. This law holds true, Newton laws holds true in inertial frames of reference only. Okay, so what is inertial frame of reference? It is vice versa like of thing, my dear friends. Any frame of reference which holds Newton laws of motion true, they are inertial frame of reference. Now the question is, what is inertia? Okay, we will understand what is inertia. Newton's first law is often referred to as the law of inertia. So the first law itself is called, what is the name of the Newton's first law of motion? It is law of inertia. Inertia, see my dear friends, everything, everyone in this universe have the inertia. Arey Baba, we will read it tomorrow, yeah. No, don't worry. That is inertia. Let us read now itself. No. We will read it. Inertia. So, inertia in mind, inertia in physical state. So, inertia, it want to stay constant in its original position. A person who is habituated to get the first rank, he don't want to stop. If you go to him and say, "Arey yaar, why you are continuously getting first rank? Why don't you wait and read tomorrow and day after tomorrow, even a supplementary exam?" No. He will say, "No, yaar, I can't." So inertia. So, this is a condition necessary for the uniform motion of a particle relative to an inertial reference frame is that the total net force acting on it is zero. Of course, my dear friends, my example is not suitable for a physics example. I talk about the inertia of the mind, but physical inertia is different. A body which is already in constant motion, A body which is already in constant motion, it will not stop unless and until some external force is acting upon it. A body which is at rest, the point you please remember that a rest is also a motion, my dear friends. See, it is moving at zero velocity. Okay, so there is a good question in general knowledge question for physics people. See, the question is like this. What I can say, a dabba in English, I can say this. A box or a bell. A bell is tied to the tail of a cat. Okay, so at which velocity cat should run, so that the sound, the noise created by that box is not here. So the velocity is zero. Like that, a stationary object means it is also moving, but the velocity value is zero. The object that is in motion will not change its velocity unless the force acting upon it. So this is see, my dear friends. See, you can see the beautiful sun and the earth, and in between a small kind of things are also is visible. They are other planets revolving around the sun. They are the Venus and Angaraka are all there. This is the picture taken very nearer to the earth, so you can see the small dots. I will make you to recognize it easily. So this one you may able to, Mercury and Venus are there. Moon, Mercury, Venus. Okay, so the sun. So because why these planets are revolving around the sun? That is the question. They are already in motion. Unless and until some external force is acting upon them, they keep on in that motion only. That is the answer, my dear friends. Because they have the inertia. They don't want to change its state of motion. Because they are moving, they keep on moving unless and until some external force is acting upon it. Okay, so this is how. So now the COVID is the external force which may make even the brightest student to stop studying it. Okay, like that. Of course, jokes apart. So the inertia. Okay, right. So this is an object. How long it is in stationary? As long as someone is applying some force, some external force acting upon it. So like that. So this is known as the uniform motion. An object continues to do whatever it happens to be doing unless a force is exerted upon it. If it is at rest, it continues in a state of rest. Okay. If an object is moving, it continues to move without turning or changing its speed. This is evident in space probes that continuously move in outer space. So changes in motion must be imposed against the tendency of an object to retain its state of motion. Okay, changes in motion must be imposed against the tendency of an object to retain its state. In the absence of the net forces, the moving object tends to move along a straight line path indefinitely. So this tendency, this nature, this property of the material, the matter, the object is called inertia. Okay, a property of an object of material, every object which is having the mass it possesses inertia. It is not opposing motion, it is opposing change of state of motion. If it is at rest, it don't want to come away from the rest state, unless and until some external force is acting upon it. If it is already in motion, it don't want to lose its motion state. So that is important thing. Then Newton placed the first law of motion to establish frames of reference for which the other laws are applicable. However, Newton implicitly referred to the absolute coordinate of the cosmos for this frame. Absolute coordinate of cosmos for this frame. Newton placed the first law of motion to establish frames of reference for which the other laws are applicable. Since we cannot precisely measure our velocity relative to a fast star, Newton's frame is based on a pure imagination. See, my dear friends, this is the most important thing. Please don't get confused. It is a pure imagination, not based on the measurable physics. So these things you will not get generally in our textbook. Please note it down. Since we cannot precisely, why? Because precisely it is not possible to measure our velocity relative from first star. Precise velocity measurement is not possible. Newton's frame is based on the pure imagination, not based on the measurable physics. The Newton's first and the second law are valid only in an inertial reference frame. Any reference frame that is in uniform motion with respect to an inertial frame is also an inertial frame. Let me read it again. Any reference frame that is in uniform motion with respect to an inertial frame is also an inertial frame. What does it mean? Say, for example, if you have a reference frame which may be fixed at the center of the sun, if it is inertial frame, that frame is inertial frame. So any other frame, not just fixed into a frame fixed to earth or only one, any other frame which is in motion, constant with respect to that frame of reference, constant velocity, if that frame of reference is moving, so that frame of reference will act as considered as the inertial frame of reference. So the Newton's second law states that the rate of change of momentum of a body is directly proportional to the force applied, and this change in momentum takes place in the direction of the applied force. F bar equal to dp bar by dt, that equal to d of mv by dt. So the second law can also be stated in terms of an object's acceleration. F bar equal to m into dv bar by dt, that equal to m into a. Thus, the net force applied to a body produces a proportional acceleration. In other words, if a body is accelerating, then there is a force on it. Defining the term 1 unit of mass by a specified stone. Defining the term 1 unit of force by a specified spring with a specified length. So, and measuring by experiment or providing by theory that force can be added as a mathematical vector. Finally conclude that F bar equal to m into a. These steps hint the second law is a precious feature of nature. The second law also implies the conservation of momentum. When the net force on the body is zero, the momentum of the body is constant. Any net force is equal to the rate of change of momentum. Any mass that is gained or lost by the system will cause a change in momentum that is not the result of an external force. So Motis, 1729 translation of Newton's Latin continued with the Newton's commentary on the second law of motion. If a force generates a motion, a double force will generate a double motion. A triple force, triple the motion. Whether that force be pressed all together and at once, or gradually and successively, and this motion being always directed the same way with the generating force, if the body moved before is added to or subtracted from the former motion according as they directly conspire with or directly contrary to each other, or obliquely joined when they are oblique, so as to produce a new motion compounded from the determination of both. Okay.
This is the translation. Okay, so an impulse J bar occurs when a force F bar acts over an internal of time delta t, and it is given by J bar equal to integral delta t into ft. So since force is the time derivative of momentum, J equal to delta p, that equal to m into delta v, this relation between impulse and momentum is closer to Newton's wording of the second law. Impulse is a concept frequently used in analysis of collision and impacts. The third law states that all forces between two objects exist in equal magnitude and opposite direction. If one object A exerts a force Fa on a second object B, then B simultaneously exerts a force Fb on A, and the two forces are equal in magnitude and opposing direction. Fa equal to minus Fb. The third law means that all forces are interactions between different bodies or different regions within one body. If some situations the magnitude and direction of the forces are determined entirely by one of the two bodies, say body A, the force exerted by body A on body B is called the action, and the force exerted by body B on body A is called the reaction. This law is sometimes referred as the action-reaction law. This is the third law, my dear friends, and Fa bar called the action and Fb bar the reaction. See, my dear friends, please recognize this Fa, Fb are written in the bold letters. That means even I am reading them as the Fa bar and Fb bar. Please don't forget to write the vector notation in your exam, at least for the first semester. So if you forget that, you will get 0. You will be awarded 0. In other situation, the magnitude and the direction of the forces are determined jointly by both bodies, and it is not necessary to identify one force as the action and the other as the reaction. The action and the reaction are simultaneous. See, my dear friends, if action is happening today, reaction will not happen tomorrow or day after tomorrow. Like in movies, something bad is happened when the hero is not even born, or even he was very small child. By the time he grows up at 25 or 35 age, he takes revenge on the villain. Okay, so that is the reaction. No, it is not happening like that, my dear friends. Action and reaction both are simultaneous. Okay, both are simultaneous. They are not separable, they are inseparable. The two forces in Newton's third law are of the same type. Example, if the road exerts a forward frictional force on an accelerating car's tires, then it is also a frictional force that Newton's third law predicts for the tires pushing backward on the road. When a person walks, they push against the floor and the floor pushes against the person. So actually what is happening, so I used to say when I was a student, I used to say, see, my dear friends, it is not the earth is attracting me, it is me who is attracting the earth. Of course both are the okay, so in a good mood like that, it is you and whenever you are moving forward. Actually what is happening, you are actually sending the earth back, so pushing the land under your feet backwards. So even we used to feel that when we were kids, when we are traveling in car or bus, so what we used to say, the entire trees and everything is going backward. Yes, we are right. No, we are not moving forward. It is the things we are sending them backward. Okay, so that's it. In swimming, a person interacts with the water, pushing the water backwards, while the water simultaneously pushes the person forward. If you don't push the water backward, water will not push you forward. So, my dear friends, applying it to your examinations, so unless and until we read the book will not make you to pass. It is you who should read the book. It is the book which make you to pass. So that's like the just for the joke purpose, both the person and the water push against each other.
So the reaction forces account for the motion in these examples. These forces depend on friction. Person or car on ice, for example, may be unable to exert the action force to produce the needed reaction force. Newton's laws are applied to objects which are idealized as a single point masses, in the sense that the size and shape of the object's body are neglected to focus on its motion more easily. This can be done when the object is small compared to the distance involved in its analysis, or the deformation and rotation of the body are of no importance. In this way, even a planet can be idealized as a particle for analysis of its orbital motion. What does it mean, my dear friends? See, Newtonian mechanics or laws of motion of the Newton is not applicable for the normal objects, normal day-to-day living objects. They are idealized, so they are basically theoretical. The theory developed by the Newton is not are not applicable exactly 100%, are not applicable to the day-to-day life objects. So they are idealized. They are the mathematical equation developed by the Newton. They are the concepts. So they are particles. They are infinitesimal particles. The mass and everything. So even the planet, if you are talking about the motion of the planet, you should not talk about the size of the planet. The entire mass should be considered as the concentrated at the center of the planet. So that is. So its orbital motion around this star and everything. So this is one limitation, and in their original form, Newton's laws of motion are not adequate to characterize the motion of rigid bodies and deformable bodies. Leonard Euler in 1750 introduced a generalization of Newton's laws of motion for rigid bodies called Euler's laws of motion. So whatever the laws of motion we are employing to understand the motion of the normal objects, it is the Euler laws of motion, but not the Newton laws of motion. If in our competition exams, which laws of motion are used to explain the day-to-day life objects, please don't put Newton. It is Euler. So later applied as well for the deformable bodies, assumed as a continuum. Okay, so this is all for today, my dear friends. If you have any doubt, you are free to ring me and ping me on my mail, and you can leave a comment on the comment box. This is all for today. Thank you.